Good evening, all of you. See the question. A 6-pole lap 1 DC machine has armature conductor 720. Z is given 720 conductors and it is drawing a current of 50 amperes from supply. What is the flux distribution produced by armature reaction per pole? So here given shape. Armature flux distribution means here this is they are asking actually about MMF. Armature MMF. What is the shape of armature MMF? Triangular. Okay. The shape of armature MMF is triangular. So we can strike out the AB and we need to find what is the ampere turns. Is it 500 or 1000? Ampere turn per pole. Armature reaction per pole means it is ampere turn per pole we need to calculate. So what is ampere turn per pole is what is the current in each conductor? Current in each conductor. So try to remember winding diagram, windings, lap and wave winding. Current in each conductor is IA by A. Okay, that is ampere. Current in each conductor I'm writing. IA by A is the current in each parallel path or each conductor. Both are same. Ampere turn. Can we write turn means Z by 2? Turn. Number of turns, half of the conductors. Ampere turn. See, IA by A is current. Ampere turn is Z by 2. Per pole is 1 by P. Now use this equation. ZIA by 2AP. This is called armature ampere turn per pole. Remember? So anyhow, we will see in the next topic, that is armature ampere turn per pole. This is equals to conductors given 720. The conductors are 720 and current IA is given 50 divided by 2A. As it is lap connected, A equals to P, that is 6. 6, P also 6. Calculate this, how much we get. Yes, 500 ampere turn will come. 500 ampere turn. And shape is already we know. What is the shape of that armature MMF? Triangular shape. MMF shape is triangular. So option C is correct. Shape is triangular. That is you have to consider first. After that, ampere turn calculation. Okay. See this question. What is answer for this? Assuming uniform distribution of current over the armature surface conductors, the shape of resultant armature MMF space of a loaded DC machine is a, so you need armature MMF shape, that's it. Triangular. Triangular with its peak along which axis? Interpolar or polar? Triangular with its peak along interpolar axis, but not polar. Along the polar axis, it is 0. So peak is along the interpolar axis. So yes, option A is correct. The peak of the armature MMF is, see anyhow this how armature ampere turn per pole, in the next topic we will see that is okay, how to find that armature ampere turn per pole. Ampere means current. What is the current in each conductor? IA by A. Okay, you have to remember windings, lap and wave winding, otherwise you cannot answer. Current in each parallel path, current in each conductor, both are same, that is IA by A. Ampere. Turn means Z by 2. Turns, how many turns? Turns formula is what? Z by 2 only. That is I written. Per pole means divided by Pi taken. That is ZIA by 2AP. That's it. Okay. Yes, interpolar axis is nothing but GNA only. What is this? In DC machines, the field flux axis and armature MMF are respectively along which axis? Main flux and armature flux. Main flux along which axis? Always direct axis. Main flux is along direct axis. Armature flux lies along which axis? Yesterday we had drawn figures. Armature flux along Q axis, south north pole. That is, armature flux always lies along Q axis. Okay. Main flux is D axis. See, direct axis, we don't have indirect axis. Don't confuse in that. Direct axis and interpolar axis. Or direct axis, quadrature axis we have. Okay. Option B is correct. In examinations we do mistakes here itself, so wherever the questions are very easy, that questions only we do mistakes. Direct axis, and we don't observe what is this. So we can also place this indirect axis. Indirect we don't have first. Direct axis, quadrature axis, or direct axis, Q axis we call interpolar axis. So this is correct. So whenever machine starts, armature reaction also starts. No, because armature reaction will takes place only under load condition. Suppose generator started, that means that there is no armature reaction because it depends on load also, whether there is load connected or not. Okay. If you connect a load, there is a armature reaction. Suppose no load. No load condition, what is the current in generator? Very, very small, negligible. Then there is no armature reaction. Okay. Okay. Next. Right. Starting calculation of demagnetizing and cross magnetizing, and cross magnetizing ampere turn per pole. Cross magnetizing ampere turn per pole. Demagnetizing and cross magnetizing ampere turn per pole. So when we get demagnetizing, whenever you shift the brush in the direction of generator, there we have additional demagnetizing effect. Now there are total in the armature we have number of turns or number of conductors. Now in the total turns, how many turns or how many conductors causing demagnetizing effect? How many conductors are causing cross magnetizing effect? So that we need to calculate. That's why I am considering, let the brushes are shifted in the direction of generator. The brushes are shifted in the direction of generator. In the direction of generator. So what is the figure? Actual brush positions is this. See, actually, where is the brushes? Every time we are drawing on armature, actually brushes is located on commutator, not on armature. But every time we draw on armature, why? Because commutator also in front of the armature, and size of the commutator is small. Here commutator is there, and on the commutator here we have brushes, but not on armature. But every time we represent on armature, okay, because we cannot draw that three-dimensional picture, no. That's why we represent on armature it is, but actual brushes is on commutator. Let this is the brush axis before shifting. This is brush axis before shifting. There are number of conductors. Under North Pole, so here we have poles. That it is South Pole. Under North Pole, current is cross. So generator direction is clockwise. So I'm not indicating. You know that clockwise. This is cross under North Pole. Dot under South Pole. Okay. Now GNA fixed one, but under load condition, MNA is here. This is our MNA, magnetic neutral axis. MNA. Now shifting the brushes onto this MNA axis. Shifting the brushes onto this by some angle theta. Okay, an angle theta shifted. Whatever MNA shifted theta, same angle brushes also shifted. Now brushes shifted by same angle theta. Okay, theta it is. Now with respect to brush position, current will change. Now change the current here, cross, here, dot. Now in order to find this demagnetizing and cross magnetizing, let us consider another angle in the opposite direction, in the motor direction. We are not shifting brushes in motor direction, just considering the angle, that's it. Let the same angle theta in this direction, theta, same angle theta. Same angle theta taking in motor direction. Now, after considering same angle theta in motor direction, observe now. Observe. The conductors present in the angle 2 theta, this 2 theta. The conductors present in this angle 2 theta and the conductors present in this angle 2 theta will produce a flux exactly opposite to main flux. Apply here. See, for these two conductors, there are two slots now here. Assume that two conductors. For these two conductors, apply right hand thumb rule. Apply right hand thumb rule. Current. Thumb indicates current. Four fingers indicates flux. Thumb is going inside the paper and your four fingers rotate clockwise. Now the flux due to these conductors is clockwise direction, like this. Clockwise. By right hand thumb rule it is. Okay. Similarly, apply for these two conductors at the bottom. Current is outside, dot. Flux is anti-clockwise direction. Like this, flux is rotating. Flux is anti-clockwise. Now, if you observe these two conductors, these two bottom and top, 2 theta, 2 theta, the flux produced by these conductors is opposite to the main flux direction or not. This is main flux, north to south, like this. Actually, it is coming. But these conductors are mainly causing demagnetizing. So it is opposite. So don't say that this line is same direction, this is only opposite. So overall effect you have to consider. Overall, the flux here is coming opposite to main flux. And here the flux is coming opposite to main flux, like this. Flux is coming, the flux produced by these conductors is opposite to main flux. So these conductors are causing a flux opposite to main flux. That's why these conductors we call demagnetizing conductors or demagnetizing turns. Demagnetizing conductors or demagnetizing turns. Okay. Now totally in the total armature 360 degrees. In total 360 degrees, how many turns or how many conductors producing a flux opposite to main flux? 4 theta or not? Yes, here 2 theta, here 2 theta. Total 4 theta angle. In 4 theta angle, whatever turns are there, they are producing flux opposite to main flux. That's why these turns we call demagnetizing turns, because flux opposite to main flux. In the same way, you observe here the remaining here, these 3 conductors are these 3 slots, and these 3 slots, whatever the conductors are present in these 3 slots, they are producing a flux by applying right hand thumb rule, and here also they are producing a flux by applying right hand thumb rule anti-clockwise it is. Now these flux lines produced by these 3 conductors mainly exactly perpendicular to main flux or not. These feed lines perpendicular to main flux. This is main flux, but armature flux coming exactly perpendicular to that. That's why these conductors we call cross magnetizing turns. Cross magnetizing in nature or cross magnetizing conductors. Clear? In the total armature, some turns are causing demagnetizing, some turns are causing cross magnetizing after shifting the brush. Now we have to find how many turns are demagnetizing, how many turns are cross magnetizing. That is we call demagnetizing and cross magnetizing ampere turn per pole. That we have to calculate. Okay, first complete the figure. Take the figure first. Quadrature axis different, direct axis different. Quadrature means brush axis or interpolar axis. See, only theta, but why 2 theta? If you take only theta, you cannot find total demagnetizing. That's why we assumed one more theta in opposite direction, because motor direction, this is generator direction. Then we got total 2 theta. In that, whatever the conductors are present, they are producing a flux exactly opposite to main flux. That's why we taken another theta in motor direction. Practically, we cannot shift the brush. We cannot shift, not possible practically. These are all theoretical analysis. Yes, for flux direction, apply thumb rule, right hand thumb rule. Armature reaction is calculated in terms of armature reaction. That is, armature reaction is due to armature flux only, no? That's why we will calculate in the armature flux how much flux is demagnetizing nature, how much flux is causing cross magnetizing nature. Okay. How cross is perpendicular, no? That yes, brushes we cannot shift, but theoretically we can say if you shift the brush, we can reduce the spark. But practically we will reduce the spark. So in the coming topic it will come. There you will observe. Okay. See now. See, right hand thumb rule. Apply right hand thumb rule for these 3 conductors. How can I show here? For these 3 conductors, apply your right hand thumb rule. Thumb is current direction. Thumb cross means going inside. Now your 4 fingers, however they are curling, your 4 fingers, In the same direction, flux is rotating. That is I drawn. It is flux direction. And here dot means current coming outside. Now your 4 fingers apply in your book, then you will get anti-clockwise direction. Flux direction is by right hand thumb rule or grip rule. Okay. Right here. Write one statement. The conductors are turns. The conductors are turns present in the angle 2 theta. Present in the angle 4 theta. 4 theta. Why 4 theta? 2 theta at the top and 2 theta at the bottom. 2 theta plus 2 theta. The conductors present in the angle 4 theta. So how they are producing flux? Opposite to main flux. In the angle 4 theta, producing a flux in opposite direction of main flux. In opposite direction of main flux. Hence, these are demagnetizing in nature. Hence, these are demagnetizing in nature. They are demagnetizing in nature. Therefore, the demagnetizing ampere turn per pole. The demagnetizing ampere turn per pole. How many turns are causing demagnetizing? That is we are calculating per pole. This is we represented as ATD per pole. This is we call ATD per pole. ATD means demagnetizing ampere turns. Now, first, total armature ampere turns how much? So here, total armature ampere turns. Total armature ampere turn per pole. Tell me how much it is. Ampere, total armature ampere turn per pole means ampere turn per pole. Ampere, what is the current in each turn? That's why every concept is interrelated. If you don't know about lap and wave winding, you cannot understand here. So there I given clearly current in each conductor or each parallel path, both are same. What is the current? Ampere. What is that current? IA by A. Current in conductor, current in turn, both are same only. If there are 25 conductors, means how many turns are there? 12.5 turns. Same current only na there. So ampere means IA by A. So all of you clear this point? Current in each turn or each conductor is IA by A. Okay, ampere over into turn. There are total Z number of conductors in armature. Then how many turns are there in that? How many turns are there? Z by 2 turns are not. Yes, that is Z by 2. Ampere turn over per pole. Per pole means divided by P, number of poles. This is the total ampere turn per pole. ZIA by 2AP. Clear all of you this point? Total armature ampere turn per pole is this. ZIA by 2AP. Okay. Clear? Next, demagnetizing ampere turn per pole. In total means 360 degrees. Total armature means 360. In the 360, how many turns causing demagnetizing? 4 theta angle. Means that demagnetizing ampere turns 360 minus 4 theta out of 360 degrees. Is it clear? How much angle turns causing demagnetizing? 4 theta. 4 theta. See, this is 4 theta. Okay, 4 theta here. In how much angle? 360 degrees. 4 theta angle conductors are turns producing flux opposite to main flux. That's why 4 theta out of total 360 degrees into ZIA by 2A. Out of the total armature ampere turns per pole, this many conductors or turns causing demagnetizing. Clear now? 4 theta by 360. This is I am writing as 2 theta by 180 into ZIA by 2AP. ZIA by 2AP. Okay. This is ATD per pole. Now you may get doubt. So still we can cancel theta by 90. I will write. Yes, you can write, no problem. Theta by 90 also you can write. But I will write in standard form 2 theta by 181. Why? Because we are expressing ampere turn per pole. Per pole, always how much angle one pole? 180 degrees. Each pole is carrying 180 degrees electrically. That's why I will write 2 theta by 181. Theta by 90 also correct. But I am writing in standard form 2 theta by 180. Okay. Next, similarly, cross magnetizing ampere turn per pole. Now you can write how many turns causing cross magnetizing? 4 theta demagnetized. So remaining 360 minus 4 theta. Okay, right here. Next, the cross magnetizing ampere turn per pole. Cross magnetizing ampere turn per pole. So this is we indicate with ATC per pole. Then how to find this? Out of 360 degrees, already 4 theta over demagnetized. Remaining 360 minus 4 theta divided by 360 degrees into ZIA by 2AP. ZIA by 2AP. Clear? Now it is, I am still little simplification. 180 minus 2 theta divided by 180, because per pole I am expressing ZIA by 2AP. This is the formula for ATC per pole. And in this equation, the important is theta. The theta always electrical angle. You have to substitute electrical angle. If they given in question mechanical angle also, don't substitute. If they given mechanical, calculate electrical. Theta electrical is P by 2 times of theta mechanical. Okay, like this. See, why are you confusing? First we calculated total ampere turn per pole. Total ampere turn per pole, armature, ZIA by 2AP. Is it clear now? Now in the total ampere turn per pole, how many ampere turns per pole causing demagnetize? This 4 theta. That's why I multiplied 4 theta out of total 360 degrees, 4 theta angle, because uh, total area is total ampere turns is ZIA by 2AP. In the total ampere turn per pole, how many turns producing demagnetize? The turns present in 4 theta angle out of 360 degrees. That's why 4 theta by 360 into that total ampere turn per pole. If you multiply this total ampere turn per pole, that means what? 4 theta only. In this angle, whatever is there, that much only you will get the answer. Okay. And cross magnetizing remaining 360 minus 4 theta. The remaining turns will produce cross magnetizing. That's why we are multiplying this ZIA by 2AP. Otherwise, how can we find ampere turn per pole? Okay. Right now, one question on this. Read the question. A 10 kilowatt, 220 volt, 4 pole, lab connected DC generator has 500 conductors. 500 conductors. If the brushes in generator shifted by 4-degree mechanical, then calculate ATD per pole and ATC per pole. So if you add both, you will get total ampere turns anyhow. Add ATD per pole and ATC per pole, you will get total ampere turn per pole. Calculate this ATD per pole and ATC per pole. Direct substitutions. But here current is not given directly. Power rating I given, voltage rating given. Now using that power and voltage, calculate the armature current. How much? Armature current 10 kilowatts, 10k divided by 220. How much armature current? Armature current how much? Yes, it is 45.45, right? 45.45 amperes. This is IA, armature current. And one more is given mechanical angle in this. So you have to find electrical angle. What is theta electrical? P by 2. Poles are 4. That's why 4 by 2 into mechanical is 4. 4 degrees. This is 8 degrees figure. So electrical angle is 8 degrees. Now given 500 conductors are there total. Therefore, calculate ATD per pole. ATD per pole. Formula is 2 theta by 180 into ZIA by 2AP. ZIA by 2AP. Calculate 2 theta by 180 into Z 500. IA is 45.45 divided by 2 number of parallel paths lab connected it is, as it is 4, P also 4. How much ATD per pole? ATD per pole how much? Yes, 63.125, right? 63.125 ampere turns. Okay. Similarly, find ATC per pole using the equation. Similarly, ATC per pole. 180 minus 2 theta by 180 into ZIA by 2AP. Calculate this. 180 minus 2 into 8 by 180 into ZIA by 2AP. 500 into 45.45 2AP. What is the ATC per pole? ATC per pole 678, right? 678 or 647? Check it is once. 647, right? 647 is right. So most of you got 647 ampere turn. This is correct. Yes, 647 ampere turns. Next, one more question. Completed all of you? Yes, in your batch, response is very fast. That is required in online class. But in some batches, particularly in Gen Code Transcode PSU batch, Response will not come if I ask for 3-4 times also. Very good. You said correct. Integer or whatever it is, you may get any, because these are all just values we are giving. No, theoretically anything we can give, anything we can calculate. Okay, anything, integer or fraction, whatever you get, right there. Yes, tomorrow and day after tomorrow also you have class full day. Okay, good. Yes, ATD per pole, ATC per pole, sum of these two will be total ampere turn per pole. You will get same. So other theta is taken to find demagnetizing. Otherwise, demagnetizing we cannot find. That's why we considered that. Mostly up to Saturday it requires. Tomorrow and day after tomorrow we have full day, that is 2 to 8:30. Yes, you can continue, no problem. But up to armature reaction is over, you cannot understand maybe because yesterday you didn't attend. So after completion of armature reaction, we go to commutation. From there you can understand. Yes, tomorrow is puja. Yes, no problem because afternoon only no class. Okay, no problem. As you wish. Day after tomorrow, if you required 2 to 8:30 actually. So accordingly, I will take. Okay. So mostly 2 to 6:30 like that. Okay. Not day after tomorrow. Mostly Saturday. See, mostly up to Saturday we take for DC machines total. See, it is not for 1 or 2 members. No, that's why. Long sessions in 2 parts. Long session means 3 hours. Is it possible to sit? No problem. If you miss also, no problem. In the next day, whenever you are free, that recording video at least you can watch. No? So those who have work on day after tomorrow, you watch on the next day morning itself and continue in the evening. So it will be no problem. Okay. Yes, day after tomorrow. Okay, no problem. You can watch because if it is offline, no, you have to face problem if you miss. But online, that is an advantage. So if you miss today, at least by tomorrow we can complete that. So if anybody miss today, suppose at least by tomorrow, if you want to attend, complete in the morning session itself that recording session, recording videos, so that you can continue without gap. But once you take a gap, 1 or 2 days, definitely you cannot regain it. Is okay. So 1 day gap means no problem, but 1 or 2 days or 3 days gap is there. Definitely you cannot. Write the question. A 6-pole DC shunt generator has 540 conductors. 540 conductors with current per conductor with current per conductor is 20 amperes. If the brushes are shifted, if the brushes are shifted by 12 degree electrical, then ATD per pole is dash. Then ATD per pole is dash. So only one. ATD per pole is dash. Try the answer. Generally, some students said in online it is very difficult for us, or regularly we are watching continuously means we are getting eye problem. So at that time I said generally okay it will happen, but I neglect it. But now I am facing the same problem because from 10 days I am taking 2 to 9:30. That's why now I am facing the effect what you people are saying. That is true. See, no one is giving correct answer. Yes, I think all of you fetching for lab connection or wave connection it is. For that, all of you fetching, no? Lens got blue lens, very good. All of you fetching for lab or wave? Not required in this question. No need of lab, no need of wave. You can solve. You can solve like that only I given. Yes. Answer is no one given till now. All of you giving 120, 60. The exact answer, no one given. No one given till now. No need lap or wave. No need of lap or wave here. Still you can solve. What is the answer? Okay, I think yes, I think some of you given right. Yes, right. Some of you given right. Yes, see here, simple ATD per pole. Some of you given right it is. That is 2 theta by 180 into ZIA by 2AB. In this question, directly I given IA by A value. That's why you no need lap or wave connection. You no need lap or wave connection because directly IA by A itself I given. What I given? With current per conductor. Current per conductor or current in each parallel path, both are same. That is IA by A directly I given 20. So 2 into 12 by 180 into Z is 540. IA by A value itself 20 divided by 2 into poles, that is 6. What is the answer? Yes, given. Most of you given this now. Yes, 120, right. The answer is 120 ampere turns. Most of you given now. Very good. Clear? So you no need lap or wave. Directly I given IA by A. That's why you should know the terminology. Current per conductor, nothing but current in each parallel path. That is IA by A. IA by A value directly given. Right. Next, side heading. Next one. Methods to reduce the effects of armature reaction. Methods to reduce the effects of armature reaction. The effects of armature reaction. Methods to reduce the effects of armature reaction. Read the first method. First one. By using a strong main flux. By using a strong main flux. So how can we create a strong main flux? Because what is the armature reaction? Armature reaction. Effect of armature flux on main flux we call armature reaction. If you create a strong main flux, the effect of armature flux on the strong flux will reduce. That is the meaning. How can we create a strong main flux? Tell me. Main flux depends on excitation. Main flux depends on excitation of the machine. See, so only one pole I taken, armature winding here, and armature current is cross. What is the armature flux direction? Clockwise. Clockwise. By applying right hand thumb rule. This is armature flux. Armature flux. If you create a strong main flux, whatever the main flux is going here, if it is very strong, now the effect of armature flux on the strong main flux is less. How to create strong main flux? Here we have field winding like this. One more pole. See, like this field winding we have on this. Now this field winding you can excite separately and you can excite self excitation and separately excitation. Now let us consider separate excitation. How can you increase the strength of main flux? Tell me. By increasing field current in this. How can you increase field current? By increasing excitation of field wind. Where you can increase the excitation? Only in separately excited DC machine we can increase the excitation, but you cannot increase this is in self-excited machines. That's why there is a drawback in this method. This is suitable for only separately excited machine. There you can increase the voltage, current increase, strength of flux increase. So it is suitable for only separately excited machine. But here another drawback is, can we increase the strength of main flux whatever the magnitude you want? Can we increase the strength of main flux to any value? No, because we can increase the main flux up to some maximum value. After that it will saturate, holes will saturate. No, so there is a limitation here. So we cannot increase the flux up to any value, just we can increase little. So there is some limitations here. That's why practically we don't use this method. Okay, so right here, by using a strong main flux, right, by increasing the excitation of the field winding, write in your notes, by increasing see, if there is permanent magnets, no, we cannot control the voltages. That is the main problem. So you are asking what happens if permanent magnets we use? We can use, but permanent magnets is uncontrollable. Same magnitude you will get. But what is the advantage of controllable excitation? Electromagnets. You can control the voltages, or you can control, if it is motors, you can control the torque in motors, or if it is generator, you can control the voltages in generator. But with permanent magnets, controlling is not possible. That's why permanent magnets mostly we don't use. Electromagnets only we use. Okay, right here, what I said previously. By increasing the excitation of the field winding, the strength of main flux increases. By increasing the excitation of field winding, okay, good observations. I don't leave that. I will take it. Is now clear? By increasing the excitation of field winding, the strength of main flux increases. Hence, the effect of armature flux. Yes, very good. Hence, the effect of armature flux on main flux. The effect of armature flux on main flux reduces. It is main field strength, not armature. We don't touch armature here. Armature flux, it is not in our hand. See, armature flux is not in our hand here. Main flux only in our hand. We can do changes in main flux, but you cannot change armature flux directly because armature flux depends on armature current. Armature current depends on load you connected. If you connect more load, more current, more flux. Less load, less current, less flux. So armature flux is we cannot change directly. Okay. So next second method. Right, next second method right here. By creating rectangular holes in pole core. By creating rectangular holes in pole core. Take the figure. Rectangular holes in pole core. Where is pole core? In the field poles. This part of field pole we call pole core it is. Now in that we will create rectangular holes like this. Creating rectangular holes. Small thin rectangular holes we create. Thin rectangular holes. Now what happens with this is, tell what happens. Here there is armature current. There is armature current cross, 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 cross. Under north pole it is. Now what is the path of armature flux? Armature flux, by applying right hand thumb rule, armature flux will flow in this direction like this. This is the armature flux. Observe. Now we created thin holes here. Thin holes, nothing but air gaps is created. When there is air gaps, reluctance increase. Now when flux is passing through the gaps, through the holes, what is the magnitude of armature flux? Decrease. If armature flux magnitude decrease, now what is the effect of armature flux on main flux? Also decreases. Means armature reaction will reduce. But there is a drawback in this method. What is the drawback? There is a drawback in this method. What is that? Yes. The drawback in this method is yes, main flux also decrease. Main flux also decrease. That is the main problem of this method. So practically we don't use, there are some methods which are failures and there are only two methods finally we are using practically. Let's see what is the methods. Practically we don't use this because there is a drawback in this. Right here, by creating rectangular holes, due to rectangular holes, rectangular holes. The reluctance offered to the armature flux increase. The reluctance offered to armature flux increases. The reluctance offered to armature flux increase, comma, its magnitude decreases. Its magnitude decreases. Okay. Whenever armature flux magnitude decrease, its effect on main flux also decrease. But drawback of this method is whenever main flux is passing through that main flux, the strength of main flux also decreases. So this is not the best method. That is the drawback of this method. Okay. Is other she's asked what is by increasing main field strength, armature reaction increase equally as EMF as the induced current magnitude increase. Because here, observe, others increasing strength of main flux means we don't increase so much value. We will increase a little. Why? Because there is some demagnetizing effect. Whatever demagnetizing taking place, that we will compensate. Like that, little strength of main flux we increase, but not so much. Okay. Yes, very good. Rajendran, you also said right. Whenever there is rectangular holes, mechanical stability of pole will reduce. Yes, strength of the pole will reduce, no, because of the holes. That's why we don't use all this. Next, third one. Third method. Third one, right. By using a chamfered pole. By using a chamfered pole. Chamfered pole. By using a chamfered pole. What is chamfered pole? See here. Now I'm drawing two poles. Try to tell out of these two which pole is the chamfered pole. Out of these two poles, tell me which pole is the chamfered pole. This is first one. This is second one. Which pole is the chamfered pole? Approximately tell which pole is the chamfered pole. One or two. First one or second one. Okay, very good observed. Self-excited, we cannot create a strong flux. That's why I said it is not possible in self-excited. Yes. Second one is the chamfered pole. Approximately, if you observe here, slightly you can observe this. Okay, observe. First one, the air gap throughout the pole is same. The air gap throughout the pole is same. But in this case, approximately check here. This is having little more gap at the pole tips. At the pole tip, more gap. At the center of the pole, less gap. So in alternators also we use a salient pole rotor, which is chamfered. So chamfered meaning at the center of pole gap is minimum. At the pole tips gap will be little increase. See, if you see a direct machine also, suppose in front of you there is one machine. Okay, let us open the stator part and remove the rotor part from there. Then if you okay, let us take a machine and observe the machine poles directly. You cannot observe that the poles are chamfered or not. You cannot see. You say that it is not chamfered from the distance. Suppose the machine or motor is after 5 feet away from you. If you observe, you can say that it is a normal pole, not chamfered pole. But if you go near to that motor and observe the poles, definitely there is a slight variation of gap. That is how much variation is. If it is 10 variation at the center, here you will have 11 variation. It is also 11 variation. This much small variation will be there in the gap, not so much. If it is 10 you don't have 15 here. Just slightly the poles are chamfered, so that you cannot identify it with your eye from some distance. It looks like same gap throughout that. But if you measure with scale, you can get little variation. 1 variation also enough. That is called chamfered pole. But here throughout that same 10 10 10 This is called normal pole. It is not chamfered pole, but it is the chamfered pole. Now, what is the advantage of chamfered? See, previously, due to armature reaction, what happens? Most of the flux lines is coming at the pole tips like this. Now, what happens to pole tips? Saturated. But if you take chamfered pole, there is more gap at the pole tips. So we know flux always prefers to flow low reluctance path. That's why the flux lines will not go to the pole tip. They will be travel in this area only. It won't go up to pole tip. Now, is the pole tip will saturate? No, it won't saturate. Pole tip will not saturate. If pole tip is not saturated, the demagnetizing effect is reduced. But now you will get out. Now this area will saturate, you will say. Yes, this area will saturate. But what is the pole tip area? Very, very small. What is this area? More. Means density, iron material is more here. But what is the iron here? Very small area. Pole tip will saturate immediately. But this area will saturate after some more time, not immediately. So like that little demagnetizing effect we can reduce using this chamfered pole. Okay, so practically we use this chamfered pole, but you cannot see chamfered from some distance. If you want to see chamfered, see the machine from very near and measure with scale, then you can understand it is chamfered or not. Okay, so write one point here. In chamfered pole, the air gap at center of pole is minimum. The air gap at center of pole is minimum and increases at the pole tips. Increases at the pole tips. So due to more gap at the pole tip, the flux will not take the path of pole tip. Now it is the path. In normal pole, it is going up to this one, pole tips. Pole tips easily saturated. Okay. Yes, 1 gap is enough. 1 means in the air gap so much reluctance that is. So that is enough to reduce the effect. Okay. Next, now the fourth and fifth method are the most important. So these are all. Third one at least we use practically, but first and second we never use practical. Right, fourth method. completed. Fourth one, by using compensating winding. By using compensating winding. Now here the questions are important. That is where we place compensating winding, where it is connected in series with armature or in series with field winding, where it is connected. Compensating winding. See, this compensating winding we place in the pole shoes, in the pole faces or pole shoe, both are same. See, this is the figure. So only one half I'm drawing, other half is same as it is this with opposite current direction. Now in the armature, this is generator direction. Direction of current is cross. Now armature flux is flowing in clockwise by applying right hand thumb rule. This is the path of armature flux. Okay, by applying right hand thumb rule, flux direction it is armature flux clockwise by applying right hand thumb rule. Now in this method we are using another winding, and that winding we are placing under the pole shoe. So in the pole shoe, a small holes we drill, a small holes we made, and in that holes we insert a winding, and that winding we allow to carry current exactly opposite to this armature current. If it is cross here, it will be dot here. This is dot. Okay. Now, if it is dot here, like that, we have to arrange. Automatically, it won't flow. We have to arrange that winding. Okay, such that current is dot here. Now, if it is dot, apply your right hand thumb rule for this winding. As it is dot outwards, flux will be anti-clockwise direction. Now, due to this winding, a flux will produce in anti-clockwise direction. So, this is the flux due to compensating winding, and we will produce this flux such that almost equal in magnitude, and these two fields compensated each other. These two fields will compensated each other. Therefore, there should not be any effect of armature flux on main flux. Armature flux clockwise. At the same time, we produce a flux due to this compensating winding in opposite direction with equal magnitude, so that these two compensated. But here important is this compensating winding will neutralize the effect of armature reaction in which region? We have two regions here. One is called polar region, another one is interpolar region. So this compensating winding will neutralize the effect of armature reaction in the polar region, but not interpolar region, only polar region. Why? How much pole shoe arc will cover? Is it covers total 180 degrees? No, it will cover 60 to 70% or 80%, but not total 100%. So what is the pole arc to pole pitch ratio? Pole arc to pole pitch. Pole pitch is 180 degrees. So it is approximately 0.7, 0.8 in that range will be there. Hence, it won't cover complete 180 degrees. This is interpolar. This is interpolar and this is polar axis. So wherever pole shoe or pole arc is covering, in that angle only there is effect of compensating winding. Outer means only this angle, whatever pole shoe covers, only this angle, the effect of armature reaction is compensated. But in the remaining angle, we call interpolar region, that is not compensated by compensating winding. Then who will compensate that? Interpoles. The fifth method is that. Fifth method, we place interpoles along the interpolar axis. Now, along the interpolar region, the interpoles will compensate the effect of armature reaction. So total armature reaction is compensated by both the compensating winding and interpoles. Okay, remember this point. Remember this. First, take the figure. Take the figure first. Yes, observe here. Compensating winding, who will supply current? Who will supply current to compensating winding? The compensating winding we connect in series with armature. That is important. Compensating winding we connect in series with armature. So whenever there is a current in armature, same current will also flow in this winding. Same current will flow. Okay. Now, can we connect compensating winding in series with the field winding here? In series with this field winding? No, because the compensating winding should produce a flux only when there is armature flux. Suppose under no load condition, is there armature flux? No armature flux. Then is it required compensating flux? Not required. That's why if you connect armature and compensating winding both in series, when there is armature current, when load is connected, when there is armature current, same current will flow in compensating winding. So both will produce flux at a time in opposite direction, both compensated each other. That's why compensating winding should be connected in series with armature winding, but not field winding. Okay. It won't affect main flux because when there is flux due to compensating, when there is armature flux, so at the same time both are cancelled each other. No? Armature flux produce and compensating flux also produce at a time, both cancelled. So no effect on main flux, even though there is compensating flux, as both are cancelled each other, there is no effect of armature flux on main flux. Now armature flux will not affect. Okay, suppose main flux is going straightly. Previously only armature flux is interacting with main flux deviated, but now at the same time compensating flux will come in opposite direction. That's why main flux will go straightly now. It won't affect, it won't distort. When there is no distortion, there is no spark at brush. So like that, sparking at brush also reduces. Okay. Cost will increase because additional winding we are placing is definitely cost increase. But what is important? Is it like damper winding? Not damper winding because yes, very good. Same like that only. So in damper winding, when current will flow? Hunting condition. Under steady state, is there any current in the damper winding? No current. Similarly, in compensating winding also, when there is armature current, then only both fields will produce. Okay, very good. Flux due to conductors near q axis. Near q axis, we use interpoles. So at the q axis, we use interpoles. Next method that is. So whatever the armature flux lines are there at the interpolar axis, that is compensated by interpoles. Next method that is. So I will show you this. Reduces armature reaction, but not completely eliminated. No? Compensating winding connected in series with armature always. Shaji. Okay. First, write here one point. Right. The compensating winding. The compensating winding is placed, the compensating winding is placed in the pole shoe, and connected in series with armature. Connected in series with armature. In series with armature. Hence, when there is armature current, then armature flux and flux due to compensating winding, flux due to compensating winding will produce at a time in opposite direction. Hence, they compensated each other. In the polar region. They compensated each other in the polar region. Therefore, effect of armature flux on main flux reduces. Effect of armature flux on main flux reduces. Compensating means equalize. Whatever armature flux is there in that region, same amount of flux will come in opposite direction. Both gets cancelled each other. Compensating flux will not be present always. When there is armature current, then only compensating flux. If there is no armature current, no compensating flux, because same current is going in both windings. Okay. Armature flux cancelled because what flux important for us? Main flux, not armature flux. Okay. Now there are some questions like how many turns required in compensating winding to compensate armature reaction? Okay, that question we will see after completion of these 5 methods. Number of turns required in compensating winding. How to find that we will see. Okay. Next, fifth method. This is important. Fifth one, by using interpoles. Take the figure simultaneously. Yes, very good. Salman, right. That is connected through commutator and brush only. Otherwise, directly, how can we connect rotating armature with compensating wind? Okay. Yes, not required, Sarath. If you use this method, you no need to shift the brush again. Okay, any one is enough. Completed. Figure all of you. So two-pole DC machine with two interpoles here. Interpoles. Why we call interpole is because these poles are located along interpolar axis. This is our interpolar axis. The poles are located along interpolar axis. That's why we call interpoles it is. Now observe this. Armature flux due to armature current is flowing in this way. Okay, armature flux it is. By applying right hand thumb rule, you will get armature flux direction. This is armature flux. Okay. Now we are using interpoles in this method to reduce the effect of armature flux on main flux. Now tell me from the figure, there are two interpoles here. Out of this, which one is north, which one must be south, so that effect of armature reaction reduces. Tell me, the top one is north or south? This pole. Tell me, top one. This top one is north or south, so that armature reaction will reduce. The top one. Yes, very good. Yes, right. You said right. That is south pole it is. And the bottom one must be north pole. Why? Because armature flux is coming exactly down, which is affecting main flux. Now what we do? We will produce main flux exactly, that is flux due to interpoles exactly opposite to armature flux, so that the effect of armature flux on main flux should reduces. Armature flux coming downward direction. At the same time, we are producing a flux due to interpoles in opposite direction. Now armature flux will not affect main flux that much. You are creating a field line opposite to that. That's why effect of armature reaction reduced. So here we should have north pole and here we should have south pole, interpoles. Now these interpoles is permanent magnets or electromagnets? Tell me that. These interpoles, whatever we are using, is it permanent magnet poles or electromagnets? Which is best? Tell me. Permanent magnet or electromagnet? Yes. Not permanent magnet. It must be electromagnet. Yes, electromagnet is correct. Why it is electromagnet? Suppose you think that it is a permanent magnet. Permanent magnet means even there is no armature flux, there is a interpole flux. Now main flux is there, interpole flux will interact with main flux now. Again there is a reaction. So these interpoles are electromagnets, means they will also have a winding, that is we call interpole winding. That is we call interpole winding. And who will supply current to that interpole winding now? Interpole winding, field winding means there must be a current. Now to that interpole winding, who will supply current? Armature will supply. From the armature only. However, we connect compensating winding in the same way. Interpole winding also we connect in series with interpole winding like this. So when there is armature current, same current will go in the interpole winding also. Same current will go at the same time. So armature flux interpole flux at a time produces in the interpolar region. Therefore, by using interpoles, the effect of armature reaction we can reduce in the interpolar region. In the interpolar region, we can reduce the effect of armature reaction. Okay. So interpole winding connected in series with armature. That's why when there is armature current, at a time interpole winding current also will carry current, interpoles also forms. At a time both the fields will come opposite direction. So effect of armature flux on main flux will reduce with this. But now important here, construction of these interpoles. Observe the shape of interpoles. Observe the shape of interpoles. Is it same shape? Same as main pole? No. This is the main pole, but shape of interpole is different. The shape of interpole we called taper shape. Taper shape. The shape of interpole is called taper, also called flat faced shape. Flat faced poles. Flat face. Face means this one, pole shoe. This is called flat. Flat it is. It is not have any curvature, anything. Flat it is. Okay. And it is having broad based. Broad based. Broad based. And main poles is not having broad based, but it is having broad based. Broad means base of the interpole is more, but the face is less. But what is main pole? Base is less, face is more. And one more mainly here, what is the air gap in the main poles? This much is the air gap for main poles. But what is the air gap for interpoles? This much is the air gap. Air gap under interpoles we keep more than the air gap under main poles. Main poles gap is less, but air gap under interpole is more. What is the reason for keeping more gap under interpole? Under interpole, the air gap is more. The air gap is more. What is the reason for more gap? Yes, it is mainly to avoid saturation of interpoles. Why saturation? Why interpoles will saturate? Yes, interpoles easily saturated. The reason is, what is the current in the interpole winding? Armature current. Now compared to field winding currents, armature current is very high or not? Yes. The armature currents are very high magnitude. 10 amps, 15 amps, 20 amps like that. If current is very high, what is the MMF produced? N into I. The MMF also very, very high. If MMF is more, automatically flux also more. Now how to reduce the flux? Inversely proportional to reluctance. So increase the reluctance, flux will reduce. It won't saturate. It won't saturate. So reluctance can be increased by keeping more air gap there. So to avoid the saturation of field poles, we keep more gap there. Because high currents are flowing in that. That's why we will reduce. We will increase the gap. Now you may get doubt. So without that, I will decrease the number of turns. You decrease. If you decrease also, if you decrease number of turns also, as current is very high, still MMF is high only. That's why we preferred air gap is more under the interpoles. Okay, so this is about construction of interpoles. And one more is, how many interpoles required in a DC machine? That depends on size of the machine. Suppose number of interpoles equals to number of main poles. This is for large size DC machines. Large DC machines. And number of interpoles is equals to half of the main poles. Half of main poles. This is for small size DC machine. Now don't say that when there are two main poles, is in one interpole is enough. One doesn't exist, no. If there are two poles, minimum two poles only required. Okay. Now the most important repeated question in every examination mostly is polarity of interpole. Here you answered easily. In this figure you answered, most of you given exact right answer. But now I will give one figure. Try to give answer for this. Linear representation. Let it is North Pole, South Pole. Now I am placing one interpole here. Okay. Now according to the figure, tell me what is the polarity of interpole. What is the polarity of interpole here? North or south? Tell me, is it North Pole or South Pole? Previously you said easily. Now answer this. This polarity of interpole is dash North or South? Okay. Some of you North, some of you South. Okay. Now here there is ambiguity. All of you now confused. This polarity is North. This is a North Pole. How to answer these questions? That's why two statements we have to remember. These two statements as it is in many examinations given in the options. As it is. Very important. Many times in engineering services prelims also same questions repeated. Polarity of interpole. How to answer this is observe the previous diagram. Observe the previous. Same from this diagram only we will write the definitions. Observe here. This is our generator direction, clockwise. This is generator direction. And this is motor direction. Motor means anti-clockwise, it rotates for same current. Now in generator direction, if you consider generator direction, generator or motor, same polarity it is. South only here. This one is south only. But definition statement will change. How? See, in a generator, the polarity of interpole is same as main pole. Main pole is this. Main pole, which is ahead to the interpole. Ahead means in front. In front, which main pole is there? To this interpole, which main pole is there in front? Generator direction. South is there. So south is the answer. Now, if you want to give statement for motor, suppose in terms of motor, you need to identify. See here. Motor will rotate anti-clockwise direction. Means rotor will rotate anti-clockwise like this. So the polarity of interpole is same as main pole, which is behind to this interpole in motor direction. See, motor is anti-clockwise. Now to this interpole, which main pole is behind? Behind means backside. South is there because rotor is rotating anti-clockwise now, motor case. Okay, these two statements you have to remember. Now observe this figure. I given generator indication. Means this is our armature. Armature is moving in this direction. In case of generator, you have to see ahead to this interpole. Which main pole is ahead? North. That's why it is north pole. Now, if they given motor like this, it will rotate. Suppose assume that motor it is. What is the polarity of interpole in motor direction? So in this direction, to this interpole, which main pole is backside or behind? North. So north is the polarity. Okay. So remember these two statements. Make a note of this. Note. First point. These two statements as it is will be there in options. Write the 2 points. The polarity of interpole is same as that of main pole, which is ahead means in front, which is ahead to interpole in generator direction. That is important. Generator means ahead, motor means behind. That's it. Next. Second, the polarity of interpole is same as main pole, is same as that of main pole which is behind to the interpole, which is behind means backside to interpole in motor direction. If they given motor in the question, you have to look behind. If they given generator in the question, you have to look ahead. Okay, these two statements only: ahead for generator, behind for motor. That's it. More air gap under interpole is to avoid saturation, because what is the current in interpole winding? Armature current, which is very high current. If current is high, automatically flux also very high. If flux is more, interpoles may saturate. So to avoid that saturation, we are increasing reluctance. How to increase reluctance? By increasing air gap. That's why we put more gap there. Okay. If flux saturates, there is no variation after that. Flux will not change. Saturation means maximum saturated. Suppose you saturated by listening continuously. Then what is the problem? You are watching, but nothing is going inside. No injection inside. Just you are watching. That is saturation. That is also same. Pulse is there, but no use of that. Saturated pulse. Okay. So this is about the methods to reduce effects of armature reaction. See, whether it is generator or motor, interpole same here, south only. At the top, south only will be there. Okay. Yes, break is required. So take a break. After that, we see some questions on this armature reaction. Then we go to commutation topic. Take a break. See this question. See question. A 500 kilowatts, 500 volt, 10 pole DC generator has lap wound armature with 800 conductors. If the pole face means pole shoe covers 75% of pole pitch, means pole arc to pole pitch ratio given. How much it is? 75% means 0.75. Pole arc to pole pitch. The number of pole phase conductors. Pole phase conductors means compensating winding only, that is. Pole phase conductors in each pole of a compensating winding. How many conductors required in compensating winding? That is the question. How can you find? Compensating winding, how many conductors required? What is the current in compensating winding? IA only. Same current IA will flow. So compensating winding will neutralize the effect of armature reaction in polar region. What is the polar region? How much? 75%. One pole totally, pole pitch is 180 degrees. In that 75% pole face is covers. Means in that 75% only it will neutralize the effect of armature reaction. So what you have to do is calculate total armature ampere turn per pole. Total armature ampere turn per pole, calculate. Multiply that armature ampere turn per pole with pole arc to pole pitch ratio 75%. So that much only compensating winding will compensate. Okay, so calculate first armature ampere turn per pole. Armature ampere turn per pole. How much it is? ZIA by 2AB. Okay, ZIA by 2AB. What is Z given? IA is not there. Use this power and voltage. Calculate IA first. IA equals to 500K divided by 500 volts. What is the IA? 1000 amperes. Armature current is 1000 amperes. Okay, now all values are there. Substitute in this. Z is 800, armature current 1000, 2A, as it is lap connected 10 poles it is. So parallel pass 10, poles also 10. Then how much it is? 4000, no, it is 4000 ampere turn per pole. Total it is. Total armature ampere turn per pole. Total means per pole, one half only. If there are two poles, for example, armature ampere turn per pole means one half. In that one half, how much pole face is covering? 75%. So it will compensate only in that 75%. So what you have to find is now calculate compensating winding ampere turn per pole. Compensating winding ampere turn per pole. How much compensating winding ampere turn per pole? Whatever pole face is there, that much. So it is total. For one pole pitch it is 4000. One pole pitch 4000. This is for one pole pitch 4000. Now pole face will cover 75% of that. So 4000 into 0.75. This much only compensating winding can compensate. Now what is that value? This is how much? 3000. 3000 ampere turns. Now this is the compensating winding ampere turn per pole. Means ampere turn it is. Ampere turn is number of turns in compensating winding, and current in compensating winding is IA only. Now I am equating N into IA, that value. IA we have already 1000. Then what is the number of turns in compensating winding? So from this, number of turns in compensating winding is 3000 by IA. IA is 1000. This is 3. 3 turns required in compensating winding. That means how many conductors? Number of conductors. 3 turns, nothing but how many conductors? 3 into 2. 1 turn has 2 conductors. 3 into 2. 6 conductors required. So answer is 6. Six conductors required in compensating winding. So clear all of you? What we did? First we calculated armature ampere turn per pole. Means one pole pitch it is. How much it is? 4000. 4000 it is. But how much compensating winding can compensate? Only in the polar region. Polar region means how much it is covering? 75%. That's why 0.75 I multiplied 3000. That is equal to number of turns into current. What is the current in compensating winding? Armature current only. That's why IA. And this is number of turns in compensating winding. First we got 3 turns. But what is the question? Number of conductors they asked. Conductors is double the turns. So that is 6 conductors. Okay, clear all of you? See, don't think why this value less means. So what can we do? Because current they given 1000 ampere. That's why turns is less. If current is less, automatically turns increase. Okay, so whatever we get, that is only the answer. Clear? See, the armature ampere turn per pole. So in this half, what is the armature ampere turns in this half? 4000 it is. This is 4000 total. Armature ampere turn per pole is 4000. And this half is again 4000. Okay, per pole 4000. But the compensating winding located in the pole faces here. It is. There are some turns in this and current is flowing. Same armature current. But this pole face is covering how much? 75% they given. See, compensating winding cannot compensate 4000. Totally, it cannot compensate. It will compensate only in polar region. Polar region is pole arc or pole face, whatever is there. How much is there? 75% only. Now, out of the 4000, 75% is 4000 into 0.75. What is the 3000? Means out of the 4000 ampere turn per pole, compensating winding will compensate 3000. Ampere turns of compensating winding 3000. That is number of turns into current. What is the current in compensating winding? Armature current only. That's why IA. There we get NC and then ZC, number of conductors. Clear now? Next question. The cross-magnetizing effect of armature reaction can be reduced by dash. What is answer? Answer. Yes, option B is correct. So this is one of the method. How can we reduce effect of armature reaction? By creating strong main flux. How can you create strong main flux? By increasing MMF. How can we increase MMF? Number of turns and field current. If you increase the field current, MMF increase, flux also increase. That is nothing but making the main field ampere turns, MMF, larger compared to armature ampere turns. So this is only correct. Remaining not satisfied. Increasing flux density under one half of the pole. Is it correct? No. If you increase flux density under one pole, saturation. That is not correct. See, due to cross magnetizing effect mainly they asked. That's why if you make pole shoes flat faced, that saturation may be reduced, but cross magnetizing will not be eliminated now. Okay. Next question. Yes, right. See, first statement is compensating winding located in the teeth cutout in main poles. So this is right. Okay. Compensating windings are series connected so that armature reaction is aided at any load. This is wrong. When you connect compensating winding in series with armature, what is happening? Armature reaction reducing, not increasing. So compensating windings are series connected for cancellation of armature reaction at any load. This is correct. Compensating windings are shunt connected. It is never shunt connected. Series only connected with armature. So 1 and 3, that is option C is correct. Right. Next topic, commutation. Completed. Next one is commutation. Commutation. So commutation is nothing but current reversal in a coil. So that we will observe in the figures now how current reversal will take place. Current reversal will take place in every coil of armature. So if you remember in the armature winding topic at the last I given one big diagram. So there we have 12 coils. 12 coils are there total. Okay. In that three coils connected in series if you observe properly with brush position. So there current will reverse in every coil. Every coil current will reverse, and that process of current reversal in a coil through commutator and brushes we call commutation process. First write the definition. In the figures I will show you how it is reversal. Write the statement first. The process of current reversal the process of current reversal in a coil. The process of current reversal in a coil through commutator and brushes. Commutator and brushes is called commutation. Is called commutation. So take the figures. So draw the figures simultaneously. Now we are considering linear representation of this commutator and brush with respect to coils. So there are number of commutator segments, number of coils in armature. That is the last diagram, armature winding diagram, that one. In that I will take some part. Some part I take it. That is some commutator segments and coils I am considering. There are number of segments. So in that some commutator segments we are considering. So these are all segments, mica insulation. So here I will show you why spark will come, how it is appears, and how can we eliminate spark in this clearly. So are you understanding this figure? If you see the last diagram in the armature winding, there are coils. Okay, there are some coils, and each coil will have some number of turns. So that is I'm taking like this coils. These are coils connected between two segments. So taking some segments in that, let A, B, A, B, and this is coils. Let it is X, Y, Z, three coils, X, Y, Z, X, Y, Z. And I'm taking in the first position, the brush is completely contact with segment A. Second position, brush is equally contact with two segments. Third position, brush is completely contact with segment B. This is the three positions with respect to commutator and brushes. Position 1, position 2, position 3. So in this figure, who is moving? Commutator is moving or brush is moving? Who will move generally? Commutator will rotate, and on that brushes we have generally rotational system. But this is linear system. Commutator is moving here, moving in this direction. Consider commutator is moving in this direction with a velocity of Vc. This is velocity of commutator. Velocity of commutator. How to find velocity? Generally commutator rotating. So we have to convert that is into velocity here. Moving in this direction with a velocity, meters per second. How to convert velocity? Velocity. What is velocity in physics? Omega r. Omega r. Okay. What is omega? 2 pi n by 60. 2 pi n by 60. Omega, speed in radians per second, converted in terms of speed, 2 pi n by 60 into radius of the commutator. Now here, I will write it is as pi d n by 60. Same equation I'm writing as pi d n by 60. This is the velocity of commutator equation. In meters per second it is. What is d here? Diameter. See, 2r I written as d, diameter. 2r I written as d. D is diameter of commutator. Diameter of commutator. N is speed of the generator or motor, anything, because generator speed means commutator also rotating same speed, n rpm. Okay, now observe. For better understanding, I'm considering current entering at the brush. Current enters at brush. Motor means current will go inside the armature. If it is generator, current will come outside. Now I'm considering it is motor. Current going inside the brush. Now you can take any value of current here. For example, I'm taking 2 IC. You can take 1 ampere, 2 ampere, 10 ampere, 100 ampere, or anything you can assume. But I assuming it is a 2 IC. And I considered IC means current in each coil. So 2 IC I taken. 2 IC. 2 IC. Current entering at brush is 2 IC. Commutator moving. It is not stationary. Commutator is not stationary. It is moving continuously. At one position, at one instant, brush is completely contact with segment A. Okay. At that time, the total current will enter into the brush. And then segment A. And now here, current equally divides because every coil will have same turns. Then current equally divides. IC in this direction, IC in this direction. Or if you take IC here, IC by 2, IC by 2. So anyway, no change. Okay. Next, after a small time, commutator little advanced. It is moving. At one instant, the brush is equally contact with two segments. Equal contact with two segments. Now tell how current will go from brush here. Current enters here. Now it is fetching that it is having same voltage drop, it is also having same voltage drop. That's why current equally divides from here itself. Current equally divides from here itself. So two IC in this direction, IC in this direction. Now what is the potential this point and this point? Same or not? See, brush drop, same 1 volt here, let 1 volt here. Then what is the potential difference between these 2 points? 0. That's why in coil Y, current is 0. In coil Y, the current will not flow, 0. That IC will go in this direction and this IC will go in the coil Z, coil Z. So IC will go in this direction, but no current in coil Y. No current in coil Y. Next, after a small time again, commutator little advanced. At one instant, brush is completely contact with segment B. Brush is completely contact with segment B only. Now total current will enter into the brush, 2 IC. Then IC will go in this direction and one more IC will go in this direction. Okay. This is for one segment. One segment commutator shifted like that continuously segment C. After that, brush will contact with segment C. So this is a continuous process now, continuously rotating commutator. Now, whenever commutator is moving by one segment, whenever commutator is moving by one segment, there is a current reversal in one coil. Check here. If there are 12 coils, 12 segments. For one segment, one coil current reverse. Like that, every coil current will reverse. Observe in these figures. In one of the coil, current reverses. Which coil that is? In which coil current reverses? Coil Y. Yes. In coil Y, current reverses. Observe. Here current is coming in this direction. Second position, current 0. Third position, current opposite to first position. This is opposite to this. So current reversal in a coil through commutator and brush. This process we call commutation process. So like that, every coil, now suppose again commutator shifted by one segment B to C, then in which coil current reverse? Z. Like that, in each and every coil current reversal takes place. That process we call commutation. Now we need a good commutation. Good commutation means current reversal taking place with no spark at brush. No spark at brush positions. That is called good commutation. But practically, there will be a small amount of spark at brush during that current reversal due to some reasons. So that reasons we will see later. Okay. Now, first of all, this commutation process will take some time or not. In order to reverse current in a coil, it will take some time or not? Yes. Now, that is called time of commutation. Now, this time of commutation we can define in two ways. What is that is? The time taken by the commutator to move one segment. The time taken by the commutator to move one segment. During that time only current reversal is taking place. The time taken by commutator to move one segment is called time of commutation. Now in another way, we can define the time of commutation by, see here, the time taken for current reversal in a coil. Time taken for current reversal in a coil is called time of commutation. Okay, in both ways we can define or not. Whenever commutator shifted by one segment, during that time only current reversal takes place. Okay, now write here time of commutation. First complete the figures. Complete the figures. Right, starting time of commutation. See, if you understand this time of commutation properly, you will get clear that why spark is coming. Okay, so I will give one small example if you understand. See this time of commutation. This is representing with TC. Time of commutation is also called commutation period. Commutation period. So what it is right statement. The time taken by the commutator. Time taken by the commutator to move one segment. Time taken by the commutator to move one segment. To move one segment is called time of commutation. Is called TC, time of commutation. How to find that? We can find this. How to find it is observe. So here each and every segment will have some width. Let WC. What is WC? Width of the commutator segment. Width of commutator segment. And this mica insulation also having some width here. Let it is WM. Width of mica insulation. Width of mica insulation. Next, this brush also having some width here. This brush also having some width. WB. WB is width of the brush. Now, how to find the time according to aptitude? Time. Time is distance by speed. Now, if you write here distance means time of commutator, time taken by the commutator to move one segment. What is the one segment width? WC divided by velocity of commutator. See here, we have to design these three terms: width of the brush, mica insulation, and width of commutator segment. So there is one design specification, that is, you should design the three such that width of brush equal to sum of mica insulation plus commutator segment width. Width of the brush should not be more than this. Width of brush should not be more than this sum. Otherwise, every instant two segments shorted. Every instant two segments started. It should not happen. So width of the brush should be equal to these two only. Okay. Now time of commutation is width of the one commutator segment divided by velocity of commutator segment. So this is approximately we can take width of the brush by velocity of commutator. Why? What is width of brush? Width of mica insulation plus commutator segment width. Then what is commutator segment width from this? Width of the brush minus mica insulation. But mica insulation is very, very small, 0.5, 0.8 mm. So negligible width that is. That's why if you neglect, approximately you can take this. So width of the brush is in meters and velocity is in meters per second. So you will get time of commutation in second. Okay. So this is the formula TC. TC you can find using these parameters. Okay, important. If you get any question from this equation only, numerical, they will give width of brush means you can use directly that. Or if width of mica insulation also given, then WC you can find by velocity. Velocity of commutator formula is this, pi dn by 60. Okay, pi dn by 60. Now observe. Time of commutation is defined as like this: time taken by the commutator to move one segment. In the same time only current reversal taking place. In the same time. If current reversal also takes place in same time, you don't get any sparked brush. If current reversal takes place in the same time, so for example, so I'm giving example, that the time of commutation I got 10 millisecond. Time of commutation I got from this calculation 10 millisecond. If current reversal also complete in the same time. In the same time, 10 millisecond, there is no spark at brush. But practically, the time taken for current reversal in a coil is more than this time of commutation. If you got 10 millisecond, current reversal will take 10.1 millisecond, little more time. That's why we are getting spark at brush. That's why we are getting spark at the brush. See the graphical representation. Let this is current in coil Y IC plus IC. It is time, and this is minus IC. For example, three positions we taken. Let it is position 1, position 2, current 0, position 3, current negative. Position 1, let us assume current is IC, one direction. That is, I am taking positive, plus IC. Positive it is. Position 2, what is the current? 0 here. Position 3, what is the current in same coil? Reverse. That is minus IC. If it is plus IC, reverse means minus IC. Minus IC. And if you join these lines, if you join these 3 points, current is changing from positive plus IC to minus IC. It is plus IC, it is minus IC. The change, current reversal in a coil Y it is. See, this time taken by the current to reverse, it is called time of commutation. If TC, whatever we calculated here, 10 millisecond, if current reversal also completed in the same time, that is called ideal commutation. No spark you will get here. No spark. So based on the time taken by current reversal, how much time the current reversal is taking, based on the three types of commutation we have. Ideal commutation, this is ideal. Current reversal and commutator taking same time to shift one segment, then there is no spark at brush. Ideal case it is. But we have two more: over commutation and under commutation. Over commutation means current reversal in the coil takes place before time of commutation. See, time of commutation is this 10 millisecond. If current reversal completed before time, then that is called over commutation. And if current reversal takes place after time of commutation, that is called delayed commutation or under commutation. Now, if you represent here, this is ideal. This blue line is ideal commutation. Now, what is over commutation is, let it is plus 10 ampere and it is minus 10. Over commutation means current reversal takes place before time of commutation. See here, it is plus 10 and here itself it become minus 10. This is the time taken for this from here to here. This is called TC, TCO. I am taking TCO. It is means time of commutation. For over commutation it is. This is over commutation. This blue TC is ideal commutation. It is. This black line is over commutation. Now practically the commutation is delayed like this. This red one is delayed commutation, also called under commutation. It is delayed or under commutation. See how much time it is taking for reverse? This much time. This is called TCP. It is. TCP means time of commutation, practically more time it is taking. Now observe carefully. Still you have confusion. Observe here. Using this equation, if I calculate the TC, I got 10 millisecond. If current reversal also takes place in the same 10 millisecond, we don't get any spark at brush. Ideal case it is. This blue line is ideal. Okay. Now practically what is the type of commutation in DC machine is delayed. Why it is? See, current reversal is taking this much time to reverse the current completely. this is more time it is taking compared to ideal case. Observe in this case, in the same time TC, how much current is reversed? If it is plus 10, this is minus 10. Now, what is this value? Minus some less than 10. Let us take minus 8 amperes. Okay, minus 8. Within that same time TC, 10 millisecond, current is reversed up to minus 8. Still, how much current is to be reversed here? Still, how much current to be reversed? 2 amps to be reversed. But already commutator shifted. Try to understand here. Commutator shifted from segment A to segment B in 10 millisecond. So in that 10 millisecond, how much current is reversed? Up to 8 amps only reversed. Total 10 is not reversed. See here. Total 10 amps is not reversed. So still how much current is to be reversed? 2 amps of current still to be reversed, but already commutator shifted. Then how that 2 amps to be reversed? How that remaining 2 amps to be reversed? That remaining 2 amps will reverse in the form of jump here. That is nothing but spark. That remaining 2 amps will jump from segment A to segment B directly in the air. That is spark. Now example for this is observe. Example. Suppose, so it will happen only in the movies, mostly 99%, very, very rare practical. Suppose there is a train. Train is there in the station. Now train started from the station. Now train will take to leave the platform, end of the platform, 60 seconds once it started. 60 seconds time it will leave. Now hero will come at the last. Now he has to catch the train. Now if he run, train started and he is also coming, and if he run continuously at same speed, he can attain or he can enter into the train in 61 seconds. He is taking the time 61 seconds to reach, but in 60 seconds train will leave the platform. In 60 seconds duration, train leaves the platform, but he will take 61 seconds to enter into the train. So at the last moment, what he has to do? If he run at the same speed up to the last near to the train, he will take 61 seconds. But train will take 60 seconds. Means it will leave the platform. He cannot enter into the train. Then at the last instant, what he has to do? That we know very well. In the movies only happen. What happened? At the last moment, he has to jump into the train quickly so that he will enter into the train. The same way here. Commutator will take 10 milliseconds to shift. But current reversal in the coil is taking 10.1 millisecond time to reverse completely. But already commutator shifted. Now how that remaining current to be reversed? That remaining current, whatever is left, that will shift in the form of spark. Now you may understand. How can we reduce the spark at brush? If current reversal in a coil will takes place within time of commutation, there is no spark at brush. Clear, all of you know? Yes, right, very good. Like a long jump. Yes, news headline. Okay, so right here, based on the time taken for current reversal, first take the figure. Hirogiri, Dadagiri. Under commutation practically never takes place. Under means current reversal before time. It never happened. Practically it is delayed. Why it is delayed, we will see later. TCO not possible. Practically not possible, just defining theoretically. TC, this is the equation. TC depends on width of the commutator segment, velocity, and velocity again pi d n by 60, diameter, speed. So like that you can find where it depends. Okay. First complete the figure. Right here. Based on time taken for current reversal, based on time taken for current reversal, time taken for current reversal, there are three types of commutation. There are three types of commutation. First, ideal commutation. Ideal commutation. Second, over commutation. Over commutation. Third, under commutation. This is also called delayed commutation. Now, what is the ideal commutation means? If current reversal takes place within time of commutation, that is ideal. No spark at that time. Okay, right here. If current reversal takes place in a coil, current reversal takes place in a coil within time of commutation, within TC, time of commutation. That is called ideal. No spark will come. And other than that ideal, any time if commutation takes place, either over commutation or under commutation, spark will come definitely. But over never happened practically, under only happens. So if here current reversal takes place, so directly I'm writing this is within TC, and over commutation is current reversal takes place before time of commutation. Before time of commutation, that is called over, but it never happened. Next, under means delayed. Current reversal takes place after time of commutation, after TC. That is called delayed or under commutation. Therefore, practically, the type of commutation is delayed. So why it is delayed? There are some reasons that we will see now. First, complete up to this. Right here. Reasons for delayed commutation. What's CP and TCP? TCP means time of commutation practically. Time of commutation TC. Practically, this is more time it is taken. Okay. Right. Reasons for delayed commutation. Reasons for delayed commutation. Reasons for delayed commutation. So there are mainly two reasons. One is see, first one is reactance voltage. Reactance voltage. Second one is cross magnetizing effect of armature reaction. Cross magnetizing effect of armature reaction. So these two are the reasons for delayed commutation. Okay, cross magnetizing effect of armature reaction. First one, reactance voltage. First, reactance voltage. Let's see what is the reactance voltage and how it is causing delay in current reversal. Delay, why it is delaying is these two reasons. Let's see what it is. Reactance voltage. So what is this reactance voltage is, in our figures previously, in coil Y current reversal is taking place. So that is I am taking coil Y current reversal takes place. Okay. So in coil Y, this is coil Y. Now during that current reversal, so initially current is going in one direction. Within short time, what is the time taken by the commutator to move one segment? That is in milliseconds. How much speed? 1000 rpm, 1200 rpm it rotates. So that is in milliseconds you get time of commutation if you calculate. Okay. So in that short time, the current in the coil is reverse. Initially current is going in one direction. When current is going in one direction, flux is in one direction. Suppose current is thumb is current direction and four fingers is flux. Or assume that here coil it is. Current is circulating in one direction. At that time, flux is like this. If current is reverse, flux also reverse. This is flux direction. So within short time, there is a change in flux in the coil. Positive, negative. That is only now here. Observe current plus IC to minus IC, just like alternating nature. Within the coil, current reversal. Because of that, flux also reverse. Whenever there is a change in flux in the coil, an EMF will induce or not? Yes, that EMF we call reactance voltage. And what is the nature of this reactance voltage? Is it statical induced EMF or dynamical induced EMF? The EMF induced due to alternating variation of flux we call static. The EMF induced due to dynamical or time invariant flux we call dynamical induced EMF. Now here, what is the flux variation? Positive, negative means like alternating variation. That's why the nature of this reactance voltage is statical induced EMF. So reactance voltage is a statical induced EMF. Remember this. Reactance voltage is a statical induced EMF. Now what happens? What is Lenz's law? What is Lenz's law? Effect oppose the cause. What is effect? EMF induced. What is the cause for this? Change in flux. What is the cause for change in flux? Current reversal. So effect is EMF, cause is current reversal. Now this EMF is opposing current reversal or not? Yes. That's why current reversal is delayed. Okay. Understand now why it is causing delay? This EMF induced in the coil opposing current reversal. That's why current reversal quickly not taking place. Slowly. That is delayed. Because of that, sparking is coming at brush. Okay. So clear all of you this point, how it is delayed? Because of the voltage. That voltage induced we call reactance voltage here. This is due to inductance of this coil. Every coil will have some inductance. Due to that, some EMF induced. That is we call reactance voltage. Okay, write one statement here. During current reversal in a coil, during current reversal in a coil, there is a change in flux. There is a change in flux which causes a statical EMF induced in the coil. Statical EMF induced in the coil. Induced in the coil called reactance voltage. Called reactance voltage. According to Lenz's law, this EMF opposes the cause. This EMF opposes the cause. Cause is current reversal. Cause, that is current reversal. Current reversal. That's why it is delayed. Otherwise, it will take place in time. Then you don't get any spark, but it is delayed. This is one reason. Reactance voltage. How to find that reactance voltage? ER equals to, how to find that with respect to inductance? L di by dt. L di by dt. This is equals to L into, what is the change in current here? IC to minus IC. Change in current IC to minus IC divided by, what is the time taken for that current reversal? Actually we call TC. Therefore ER equal to L into 2IC by TC. So it is proportional to LIC by TC. Okay. Reactance voltage is proportional to LIC by TC. Remember this relation important. How can we reduce reactance voltage? How can we reduce reactance voltage? By increasing time of commutation. Reactance voltage reduce. How can we increase time of commutation? TC equals to WC by VC. By decreasing velocity of commutator, TC increase. How can we decrease velocity of commutator? By decreasing diameter of commutator or speed of the commutator. Okay, these are all interlinked. Okay. Yes, increasing commutator segment width. Automatically brush width also increases. Yes, that is also correct. Yes, speed of commutator nothing but armature only. Both are same speed, no? Same shaft connected both. Okay, next, second one, cross magnetizing effect of armature reaction. The second reason is cross magnetizing effect of armature reaction. Second one, cross magnetizing effect of armature reaction. See, this is already we know from the previous armature reaction topic, graphical representation. So there I shown actually along the brush axis, what is the main flux? If only main flux is taken, 0. If flux is 0, is there any EMF in the coil at that time? No EMF, because during commutation process, every coil behaves as short circuit. Every coil will behave as short circuit. During that short circuit, if there is any voltage in the coil, current will flow. That current may get heavy spark also sometimes. So there should not be any EMF at that time. EMF 0 means current also 0. Then you don't get any spark. That is a safe operation. See, I will show you here. During cross magnetizing effect of armature reaction. If it is only main flux, like this. What is the flux along the brush axis exactly? 0. The main flux is 0. This is under no load condition. Only main flux is there. Then no spark you will get. No load condition, no spark. But spark is only under load operation. Because under load, current is there, armature flux, armature reaction. One of the effect is cross magnetizing effect. Due to that, distortion. So because of this now, see, this is our resultant flux during armature reaction. What is that resultant flux? If you remember, it is not becoming 0 along the brush axis. So yesterday's diagram I am drawing again here. Yesterday's figure only I am drawing. Okay. This resultant flux is not becoming 0 along the brush axis. Now there is some flux or not? Yes. Now if you consider that previous commutator figure, observe here. Segment A, segment B. Now during that, coil Y behaving as short circuit or not? Yes. During this coil Y behaves as a short circuit through brush. Short circuit only. There is a conduction throughout that. Coil Y behaves as short circuit. So during that condition, the EMF in the coil, if it is very high, the current also very high. Now, which may damage sometimes the commutator segments and brushes with heavy spark. Now, along the brush axis here, what is the magnitude of flux due to armature reaction? And one of the effect, cross magnetizing effect. Due to this cross magnetizing effect, the flux is not becoming 0. Now, when there is a small amount of flux, what is this flux? Main flux. That is time invariant flux. Due to this flux, an EMF induced in the coil still. What is that EMF? Dynamical induced EMF. Previously, there is reactance voltage. Now, additionally, this EMF also there. So, in the coil, already there is reactance voltage plus again additional EMF due to cross magnetizing effect. Now, there are two EMFs totally. Now, due to this EMF, still a current will be there, and that current will appear as a spark at brush. That current will appear as a spark at brush. Now, if this flux is 0, for example, then what is EMF in the coil at that time? 0, no EMF and no current. Then no problem to commutator and brush assembly. But due to cross magnetizing effect, as the flux is distorted, it is not becoming 0 along the brush axis. Due to that, whatever the coil coming under the brush at that instant, coil Y is coming. During that, in coil Y, there is an additional EMF due to cross magnetizing effect. Now that EMF will maintain some current in the coil. That current will appear as a spark at brush. Okay. So if you don't reduce these effects, what happens here is, observe. See, already due to reactance voltage, there is some voltage. Now additionally, there is cross magnetizing effect. If the sum of these two voltages exceeds some value, generally, whatever the mica insulation is there now here, this mica insulation will withstand approximately 20 to 40 volts, not more than that. Approximately, this mica insulation will withstand a voltage difference of 20 to 30 volts, 40 volts. If it is crossing beyond that, suppose if both sum of the reactance voltage plus cross magnetizing voltage becomes 50 volts, for example, if it is 50 volts, mica insulation damage. Then these two segments behave short. Then there is heavy spark at brush. That's why we should reduce this cross magnetizing effect and also that reactance voltage. If reactance voltage removed and cross magnetizing EMF also eliminated, then no EMF in the coil, no opposition for current reversal, happily it takes place. For that we have some methods to improve commutation. Okay, right here, 1 point. Due to cross magnetizing effect of armature reaction, the flux along brush axis, is not becoming zero, is not becoming zero. Hence, it causes a dynamical EMF induced, a dynamical EMF. Why dynamical? What is this flux? This is the flux going from north to south. That is time invariant flux. That flux will cause EMF, dynamical EMF we call, which causes a dynamical EMF in the coil, which maintains a current, which maintains a current and appears as a spark, appears as a spark at brushes, appears as a spark at brushes. Now you may get some idea how to reduce spark. Now we have to make that reactance voltage zero. Also we have to make that flux along the brush axis zero. If you made this one, you don't get any spark at brush. That is methods. So we have the methods to improve commutation now. Okay, right here. See, mica insulation is there. You check here, this segment connected to this side, connected to this side. It is like a short circuit only now. Right. Side heading, methods to improve commutation. Methods to improve commutation. So with this, commutation topic will be completed. Methods to improve commutation. So there are three methods to improve commutation. One is resistance commutation. Resistance commutation. Second one, interpole, or also call it is voltage commutation. Interpole or voltage commutation. Third, brush shifting. Practically it is not possible, only theoretically it is. Brush shifting, because in many examinations we have the questions on this brush shifting. In order to improve commutation in DC machine, in which direction brushes has to shift? Which direction? That is, which direction? Opposite to motor direction. Okay, right. First one, resistance commutation. Making the flux along brush axis zero, spark is zero. Right. The first one, resistance commutation. Resistance commutation. So what is this? Is already we know this in the construction. I said we are using carbon brush. Having high resistance, it will improve commutation. That is only this point. So resistance commutation is nothing but by using a high resistance carbon brush. By using a high resistance carbon brush. See, it is how. Let us consider the brush is made up of carbon, but not copper. Brush is made up of carbon. What is the carbon? Having high resistance. If it is carbon having high resistance compared to copper, because of that high resistance, this coil is having some inductance of the coil L, and brush is having high resistance. So during current reversal in every coil, there is a loop formation. That is RL formation or not. It is acting like RL network. In a RL network, what is the time constant of the network? Time constant, tau equal to L by R. The time constant of RL circuit is L by R. Whenever resistance is high, what is the advantage? Time constant reduce. What information you will get from time constant? Time constant. It will give the speed of the response. Suppose best example is control system. Control system. If you given a step input, that output will come, step response will come. How many or what is the how many time constants it will take for a step response to reach steady state? Tell me. You know, I think control system. From control system, how many time constant a signal step input step response will take to reach steady state? 5 time constants. Yes, 5 time constant. Suppose if time constant reduce, what is phi t value also reduce? Means quickly you will get the output response. Steady state, the signal will reach steady state very quickly if time constant decreases. In the same way here, if time constant reduce, the speed of the current increase. Quickly current reversal takes place. So little delay reduces or not? Yes. If we use high resistance carbon brush, the time constant of the coil reduce, which will improve the speed of the current response. Now quickly current reversal takes place. Little quickly, but totally it cannot eliminate. Little you can improve commutation. That's why we call it is resistance commutation. Okay, right here. By using high resistance carbon brush, high resistance carbon brush, the time constant of the coil reduces. The time constant of the coil reduces, which improves the speed of current response. Time reduces means speed increases. The speed of current response or speed of current reversal. Hence, delay reduces. Delay reduces. That's why we call it is resistance commutation. Okay. But it cannot improve, it cannot eliminate totally. The best method is second one. Interpole commutation is the best method. Second one, interpole commutation. Completed this. See now, second, interpole commutation, also called voltage commutation. It is interpole or voltage commutation. Why we call voltage is whatever voltage is there in the coil. What is the voltage in the coil? Reactance voltage and EMF due to cross magnetizing effect. That voltage we will cancel with another voltage. Voltage only cancel. That's why we call voltage commutation. How it is observed here. See, when you place interpoles, whenever we place interpoles, where interpoles are located? Along interpolar axis. Observe here. This is only main flux and brush axis. Brush axis or interpolar axis, both are same. Now, during armature reaction, if you place interpoles, let it is some north pole. Whenever we place interpoles will produce a flux opposite to armature flux. Okay, because of that, whatever the flux is there previously, resultant flux along the brush axis, now that resultant flux along the brush axis will become zero. The resultant flux will become zero. Okay, previously there is some flux here. Resultant flux is not zero along the brush axis, but now it is zero because of placing interpoles. Because of this interpole flux, the resultant flux we will make to zero by properly choosing interpoles. Okay, now this flux is zero. Whenever this flux is zero, what is EMF due to cross magnetizing effect? Zero. It will become zero now. Now there is no EMF due to cross magnetizing effect. That is zero. Now there is another voltage in the coil. What is that? Reactance voltage is there. Now how we will compensate that one is using these interpoles, the resultant flux is becomes zero, and additionally there is some flux. Additionally, flux produced by interpoles. So it is approximately flux produced by interpoles. It is approximately 20 to 30%. So additionally, the interpoles will produce some more flux. In which direction? If armature flux is coming downward, interpole flux is opposite. Now, due to this interpole flux, due to this additional interpole flux, an EMF induced in the same coil due to interpoles. Now, already there is some reactance voltage ER. Now, this polarity of EMF, this polarity of EMF, both opposite direction. Why opposite? Reactance voltage is due to internal flux, and this EMF induced due to interpoles is opposite direction, because interpoles will produce a flux always opposite to armature flux. So because of that reason, this voltage cancel each other. Whatever interpoles will produce a flux, due to that an EMF induced in the coil, that EMF gets cancelled with the reactance voltage. Now reactance voltage also cancelled. Now is there any voltage present in the coil? No voltages. If there is no voltages present, is there any opposition for current reversal? No oppositions. Then happily, smoothly current reversal takes place. Okay, that's why we call interpole, by using interpoles. And why voltage commutation is we are cancelling the additional reactance voltage using additional EMF due to interpoles. That's why we call voltage commutation. These interpoles we also call commutating poles. Commutating poles. This is also called compoles. The interpoles we also call compoles. These are all names for interpoles only. Okay. Next, last method. Last method, brush shifting. But it is not practical method, theoretically only we are defining this. Tell me now, if you want to improve commutation, in which direction brushes has to be shifted? So already we discussed yesterday it is. See, to improve commutation, which direction? To improve commutation, the brushes has to be shifted. The brushes has to be shifted in the direction of generator. In the direction of generator, or opposite to motor direction. Opposite to motor direction. So remember two statements. Okay, so already we have seen yesterday this. If you shift the brush in generator direction, resultant flux zero there. Flux zero means no EMF due to cross magnetizing. Almost we can eliminate spark at brush, or reducing. Little commutation will improve due to this brush shifting, but practically we cannot shift the brush. Yes. Okay. So this is about commutation. So with this, the main topics is over, and tomorrow we will see first characteristics of generator and motor, and then we start the most important and guarantee questions is speed control of DC motors. Okay. If you ask in DC machine, which is the most important topic for examination point of view is speed control of DC motors. 99% if you get any question, suppose two questions you got in gate, in that at least one question will be from speed control. That much important it is. Okay. So we'll see that is tomorrow. So tomorrow I think 2 to 8:30. Okay.
Sir,
Tell me.
in interpole commutation, how that interpole compensate the ER, sir? Because ER is due to reversal of flux, sir. But interpole will compensate only the armature flux, sir. How it will compensate ER, sir?
So interpole flux is always producing in the opposite direction of armature flux. No?
Okay, sir. That armature flux will produce cross magnetization alone the armature reaction, sir.
But okay, but approximately EMF induced in the coil, and is there any direction can you find directly with reactance voltage?
No, sir.
No. Then how can we
Appropriate
decide?
direction.
How can we decide?
That's only I have to ask.
That's why we consider it will cancel out in one of the half cycle. Then we will get no EMF. Reactance voltage also we are nullifying there.
Sir, and another doubt, sir. Yesterday you told while finding the armature flux inside the armature conductor, the flux direction is from south to north. When we will take south to north and when we will take north to south, sir?
You understand magnet north-south. In a magnet, when south to north, where south to north?
Yesterday we have taken, sir, in case to only
externally north to south, internally south to north. Same only, no? If it is rotor also, it is iron. Inside south to north always. Outside
okay.
north to south.
Okay, sir. Thank you, sir. That's it.
Okay.
Hello, sir.
Oh, tell.
Good evening, sir. Sir, the statical EMF and dynamical EMF.
Because reactance voltage is like statical EMF because it is induced due to the variation of current, current reversal, positive to negative. When current changing from positive to negative, what is the flux variation also? Positive to negative. Means that is like time. That is like time variation, no? Time variant flux it is.
Okay, sir. Thank you.
Then what is EMF induced statical?
Okay.
Okay.
So that the direction of flux, sir. Direction of flux again. 88 slides, sir.
Direction of flux.
Yes, sir. That you showed the reactance.
That is varying, no? Because
diagram.
current direction is changing, no? Within short time. That's why flux direction also changes, just like alternating variation.
Like sinusoidal, sir.
No, not exact sinusoidal. Like time variation is there in that. Okay.
As in the dynamics, sir.
And that EMF is due to DC flux, no? That is time invariant. Whatever resultant flux is there, that is distortion of main flux.
Yes, sir.
Okay.
Yes, sir. Yes. Okay, sir.
Hello, sir.
Tell me.
Good evening. Sir, here ER and that ECMF, that is cross magnetizing. Here, how we can know that? Because in one case, that cross magnetizing, the flux is decreasing. And another case, current is reversal. that is, sir, both polarity will be same. How we can it fast also.
Not understand. Ask again.
Sir, that EMF induced due to cross magnetizing, right?
Oh, okay.
And that E reactance will be in the same phase.
Not same phase, because we cannot say same phase now, because this is due to time invariant flux, this is due to time variant flux reactance voltage. They are not in phase.
In phase, but both magnitude, one is
Not
positive, then other will be positive.
they are not having same magnitude also we cannot define, because they are independent of flux, no. This magnitude is different, its magnitude is different, both are different.
Then when we are designing to opposite, then how we know that?
How?
Means to nullify it, then how we know that that voltage is, as you say, this will be
for example, this is we cannot show directly. For example, this is clear, no? Cross magnetizing EMF will become zero whenever flux is zero due to interpoles.
Yes.
And reactance voltage we are compensating using interpole flux, but this flux directly we cannot consider this direction, in what direction it is, because in positive of one direction, negative of another direction, we cannot define the direction for reactance voltage. Okay, that's why approximately we will consider it will get cancelled out due to interpole additional flux, but direction we cannot define.
Thank you, sir.
Like cross magnetizing EMF. Okay.
Hello, sir.
Tell me.
Sir, in compensating winding, we are using that in the pole, no, sir. Sir, if we connect that in the shunt field, is there any effect on that?
Effect means, suppose compensating winding connected in series with field winding, no?
Yes, sir.
Now what happened? Even there is no armature current, no load means armature current very less.
Yes, sir.
Then even there is no current, always field current is there, no? ISH. So
Yes,
when
sir.
there is ISH, main flux will produce, and flux due to compensating winding also produce. But is it required at that time?
No use.
Whenever there is armature flux, then only this flux is required for us. Otherwise, it is not required for us. So it is possible to generate both at a time if you connect armature winding series.
Okay, sir. Means it's not harmful of that motor.
No.
Okay, sir. One more. If we compensate the armature flux by using that, it's maybe it's decreasing the load current, no, sir?
Which one?
If we compensate the armature flux, that armature current also reduces.
No. Flux is reducing, but armature current will not reduce. No, it remains same. Current remains same, but whatever flux is produced, that effect we are reducing there. But it won't affect armature current again back. Okay, armature current remains same only.
In all cases. Okay, sir. In last method, interpolar voltage commutation. Sir, for by using that interpolar, the flux is compensating that in the another method, no, sir, that phi. But how can that extra additional force is coming? Because that additional flux only.
We have to produce that interpoles like that only, because whatever the flux is produced by interpoles, we have to arrange. It has to produce a flux opposite to armature flux. At the same time, it has to produce some additional flux. Like that, we arrange number of turns in this. Automatically, it won't produce. So we have to make that arrangement here. More flux, little more flux, so that it will produce additional EMF along that interpolar axis, means along the GNA, that is brush axis. So this flux will cause some EMF in the coil. That EMF we will consider opposite to reactance voltage. So these two compensated each other.
Okay, sir.
Otherwise, you neglect that. No need. If you are not understanding, also not required, because mainly cross magnetizing EMF is important for us. If it is zero, no, then there is no spark at brush. That is enough. Okay.
Okay, sir.
Hello, sir.
Pratish.
Sir, yesterday I have said that when the brushes are at G and M axis, the portion voltage and current are zero. But how can we extract that voltage and current outside?
That's why I said current is, we are not collecting current only from there. You observe the armature winding loss diagram. Is
Yes,
current
sir.
is coming from only one coil? Many
No, sir,
coils,
it's,
no?
yes, sir. 4 parallel paths it is coming, sir.
That is we have to consider, not one coil. We are considering current reversal in one coil here, but current is coming at brush from so many coils, so many parallel paths. That's why we should not take one brush directly, one coil.
Okay, sir.
Okay.
Sir, 75, sir. By making the holes in commutating winding, we can also reduce the 80 current in the pole shoe also, sir.
By making
that holes in pole shoe, sir, we can also reduce the 80 current, sir.
We can
also reduce the 80 current, sir. 80 current.
Already we are reducing eddy current by laminations, na, here. Already laminations are there in this.
Yes, sir. By this also effective area of the reducing,
little reduce, but not so much, na, it is. Because small holes we drill in that, not big ones, small one. Yes, it will reduce, little it will reduce, because some area is open, it is becoming air, na, here, that is open. Because of that, some eddy currents will reduce according to, right?
Okay, sir. That's it. Thank you, sir.
Hello, sir.
Tell me.
Sir, will you please explain the polarity of interpoles?
Page number. Polarity of interpole.
Yes, yes.
See, generator direction clockwise.
Yes, yes.
Now, what is the polarity of interpole here? Same as main pole. Which main pole? This one.
Yes.
Okay.
Yes.
Now, to this interpole, in generator direction, this main pole is ahead to the interpole or not?
Yes, I do that.
Suppose if you want to give the polarity in terms of motor means anti-clockwise, like this rotor will rotate anti-clockwise. Now polarity of interpole same as main pole only. Which main pole? Whatever behind to that. In motor direction to this interpole, which main pole is backside? South.
South pole.
Because
yes.
Anti-clockwise it is rotating, no?
Yes, sir. Anti-clockwise.
Okay. That's why generator means take ahead, motor means take behind.
Okay, sir.
Okay.
And sir, you have told that the number of interpoles is equal to number of main poles in the large DC machines.
Yes, yes.
Yes, sir. This statement at bottom in this slide.
This one
so,
only.
sir, what rating large DC machines we can consider in this?
Large means like you can consider 50 kilowatts, 100 kilowatts in this range. Small rating means fractional, like 1 kilowatt. So in the range less than 10 kilowatts, you can consider small. Less than 10 kilowatt DC machines. They are small one.
Okay, sir.
In labs also, whatever we use, they are small rating DC machines.
Okay, sir. So it means about 10 kilowatt, all are large DC machines we can consider.
All?
About 10 kilowatt, we can consider all large DC machines.
Yes, yes.
Okay, sir. Sir, the last second computation technique, sir. Interpole computation.
That one?
Sir, last second interpole computation. You have told.
Tell me.
Yes. Sir, will you please explain in short it once?
See, nothing. If you place interpole, no, same as in the armature reaction, same interpoles are placed. When we place interpoles, the resultant flux along the brush axis will become zero. Actually, there is some resultant flux at brush axis previously due to cross magnetizing effect. But after placing interpoles, that flux we can make zero. Okay.
Yes.
By choosing properly that flux, interpole flux, it will become zero. Once it is zero, is there any EMF in the coil at that time? No EMF.
Yes.
That's why no spark will come. Okay.
Yes, sir. And sir, what is about that ER, sir?
That is reactance voltage. No? That reactance voltage is due to change of flux in the coil. So that is you can neglect because reactance voltage is very small in the range 2 volts, 3 volts, 5 volts within this. That is a negligible voltage when compared to cross magnetizing voltage. This is very high voltage. This is only our main consideration. Generally, we neglect that reactance voltage because this reactance voltage is approximately compensated by brush drop itself. Because brush drop how much? 0.5 volts, 1 volts, 2 volts. So that
Yes,
brush
yes.
drop, whatever is there, this reactance voltage both compensated. Reactance
Okay.
voltage induced, it is dropped in the brush as a brush drop. So we will neglect that.
All right, sir. So main
Okay.
consideration is cross-magnetizing effect.
Yes,
voltage.
yes. This is only the high voltage.
Okay, sir. Thank you, sir.
Navadip.
Hello,
Navadip.
sir. Yes, I have doubt in yesterday class, sir.
बताना.
सर वो आर्मेचर एमएमएस में जो ट्रायंगल वेव फॉर्म आई है ना सर, उसमें वो 1-1 कॉइल कैसे बनाते हैं सर उसका एमएमएफ?
1-1 कॉइल बोले तो इस स्लॉट्स में जो भी है ना वो.
हाँ 1-1 लिया सर आपने.
तो ये कॉइल एक एक कॉइल का कितने साइड्स है? 2 साइड्स होते हैं ना.
यस सर.
एक कॉइल में 2 साइड्स, एक 1 1 डैश 2 2 डैश लाइक दैट. इसे हम 1 1 इसे 1 डैश बोलो. अब 1 हम किधर रखते हैं? ये स्लॉट में. कॉइल साइड
Yes,
1
sir.
को स्लॉट ये स्लाइड इसमें रख दे एंड
Yes, sir.
कॉइल साइड 1 डैश को इस स्लॉट में रखेंगे.
Yes, sir.
एग्जैक्टली जस्ट जो भी हम आर्मेचर वाइंडिंग में देखे हैं ना, कॉइल साइड्स, कॉइल 1 लैप वाइंडिंग एंड वेव वाइंडिंग में फर्स्ट कॉइल साइड इन नॉर्थ पोल फर्स्ट स्लॉट, सेकंड कॉइल साइड इन साउथ पोल फर्स्ट स्लॉट, फुल पिच वाइंडिंग दैट इज सिंपली.
Yes, sir.
सो ऐसे हम प्लेस करें ना, ये 1 1 डैश.
सर
अब
फिर
हम
वो
क्या कर,
एमएमएफ
हाँ
आपने
एमएमएफ
जो
प्रोपोर्शनल.
एमएमएफ में रेक्टेंगुलर ही क्यों लिया? वो साइन वेव नहीं होनी चाहिए सर?
साइन वेव बिकॉज यहाँ पे जो भी फ्लक्स मैग्नीट्यूड है ना, फ्लक्स वेरिएशन कैसे होता है? बिकॉज व्हाट इज द गैप अंडर द पोल एग्जैक्टली हियर? कांस्टेंट.
यस सर.
अगर फ्लक्स कांस्टेंट है तो उसका मैग्नीट्यूड भी क्या होना चाहिए? यहाँ से यहाँ तक थ्रू आउट द पोल
कांस्टेंट होना चाहिए सर.
कांस्टेंट ही रहना चाहिए ना. इसलिए साइनसॉइडल
Yes,
नहीं होता है यहाँ पे, मगर सिंक्रोनस में वो साइनसॉइडल बनेगा. बिकॉज वी यूज चाम्फर्ड पोल, more gap, less gap at the center of the pole and more gap at outer of the pole. Okay.
ओके सर. सर लेकिन जो ब्रश ब्रश एक्सिस के पास तो सर चेंज होगा ना सर वहाँ?
हाँ इसलिए चेंज होगा था ना. ओके वो आप बता रहे क्या?
यस सर. आपने तो वो डायरेक्ट एकदम ले लिया ना सर.
सो मैं इधर हम फ्लक्स नहीं ले रहे डायरेक्टली, करंट को ही कंसिडर किए थे ना.
यस सर.
यस करंट क्या हो रहा है? करंट सी करंट सपोज फॉर एग्जांपल ये स्लॉट यहाँ पे है, कॉइल यहाँ पे है, नॉर्थ
Yes,
पोल के नीचे है ना.
यस सर.
ओके इसमें करंट क्या है? क्रॉस. ओके करंट क्रॉस, यहाँ से क्रॉस है, यहाँ तक भी क्रॉस
Yes,
है, ये भी क्रॉस है, यहाँ तक भी क्रॉस आएगा, क्रॉस आएगा, क्रॉस आएगा, टोटल 180 डिग्रीज क्रॉस ही आएगा इसमें. ओके जब ये कंडक्टर
लेकिन
साउथ पोल के नीचे जाएगा उसमें करंट क्या होगा? नेगेटिव होगा.
सर मैं ये कह रहा हूँ सर, ये जैसे नीचे से ऊपर जाएगा कंडक्टर तो
हाँ.
इसमें पहले कम होगा फिर बढ़ता जाएगा ना करंट सर?
यस वो तो साइंसली होना चाहिए.
यस
ऐसे
सर.
होना चाहिए ना. वेरिएशन मैग्नीट्यूड ऑफ करंट ऐसे ही चेंज होगा ना. मगर
यस
हम
सर.
डायरेक्टली ऐसे ले रहे पॉजिटिव नेगेटिव वेरिएशन अप्रोक्सीमेटली, बिकॉज यहाँ पे पॉजिटिव है क्रॉस, यहाँ पे नेगेटिव है, तो हम वो जो भी वेरिएशन हो रहा है ना वो हम नेग्लेक्ट कर रहे हैं. वो
ओके सर.
वेरिएशन कंसिडर नहीं कर रहे हैं.
ओके सर.
सेंटर पे तो मैक्सिमम होगा करंट मैग्नीट्यूड.
यस सर.
यहाँ से यहाँ तक जब ये जा रहा है ना ब्रश एक्सिस तक, उसका मैग्नीट्यूड कम हो
फिर
जाएगा.
कम होगा सर. हाँ
यस राइट होगा. बट वी आर टेकिंग
सर.
अप्रोक्सीमेटली दिस वेरिएशन प्लस माइनस. ओके
ओके सर.
अभी क्या है?
सर एक और डाउट था सर, एक मिनट.
कहाँ से है?
सर हरियाणा से है सर.
चंडीगढ़.
हरियाणा सर.
चंडीगढ़ ही है ना कैपिटल.
हाँ सर. सर एक बार सर ये क्रॉस मैग्नेटाइजेशन वाला और बता दो सर.
इसमें
सर ये कम्यूटेशन में सर.
हाँ बताना. रीजन में
सर क्रॉस मैग्नेटाइजेशन इफेक्ट ऑफ आर्मेचर रिएक्शन में है ना सर ये.
ये
सर ये मेरे को ये समझ में नहीं आ रहा सर, ये ब्रश कैसे सॉर्ट कर देगी इसको सर, ये वाई एक्सिस को?
ये इसमें यहाँ से यहाँ तक इधर देख एक बार, ये इसे लेट एंड दिस इज वन एंड वन, ये अनदर एंड वन डैश.
Yes,
वन
sir.
सेगमेंट ये से जुड़ा है ना,
हाँ सर।
यहाँ से ब्रश से कनेक्ट है ना, फिर
हाँ
अब 1-B से जुड़ा है ना, ये बी भी ब्रश से कनेक्ट है ना, ब्रश
हाँ।
इज कंडक्टिंग ओनली ना।
अच्छा, ये दोनों एक डायरेक्टली
हाँ,
कनेक्ट हो शॉर्ट हो जाएंगे सर।
एक शॉर्ट हो गया ना, इसलिए।
सर लेकिन ऐसा नहीं होता सर, जैसे ये ब्रश का सर कोई पोटेंशियल होता सर, अगर ए में ज्यादा होगा बी में कम होगा तो सर।
अब तो वेरिएशन होगा, बिकॉज वी आर
हाँ
टेकिंग, हम डायरेक्टली ये इक्वल कांटेक्ट कंसिडर करते हैं ना इसमें। अगर एक इंस्टेंट में सेगमेंट ए से ज्यादा कांटेक्ट होगा, सेगमेंट बी से कम कांटेक्ट होगा, तभी भी
अच्छा।
ये शॉर्ट सर्किट ही बिहेव करेगा ना ड्यूरिंग दैट। ओके,
कैसे सर?
कारण अगर ये पोजीशन ले ले, थोड़ा ब्रश को इधर हटा दो, अभी भी शॉर्ट सर्किट ही है ना। मे बी ब्रश
हाँ
ड्रॉप तो
सर।
सेम नहीं है बोथ साइड्स, फिर भी ये
हाँ।
तो इससे जुड़ा है ना, कंटिन्यूअस पाथ है ना इसका,
अच्छा सर।
इसलिए।
सर रेजिस्टेंस तो होता है ना सर थोड़ा बहुत ब्रश में सर, तो चेंज
होता
होगा
है,
सर।
चेंज होगा, मगर ब्रश ड्रॉप तो हाई है, कार्बन ब्रश है, इसलिए डैमेज तो नहीं होगा। इसलिए
हम्म
जो भी अगर ईएमएफ है तो प्रॉब्लम, इसमें क्रॉस
हम्म।
मैग्नेटाइजिंग का ईएमएफ, ये ईएमएफ होने से प्रॉब्लम होता है। अगर वो इफेक्ट को रिड्यूस कर दो, इसमें ईएमएफ है क्या कॉइल में, नहीं है। अगर
नहीं
शॉर्ट
है,
सर्किट हुआ तो भी प्रॉब्लम नहीं होगा, बिकॉज अगर ईएमएफ जीरो है तो करंट भी जीरो है इसमें।
करंट ही नहीं होगा।
हाँ, शॉर्ट सर्किट से भी नो प्रॉब्लम।
ठीक है सर।
ओके।
ओके, थैंक यू सर।
So tomorrow we check. Good night.